Welcome, ladies and gentlemen, to another kata and coding challenge edition on Code Wars. And today we'll be solving the next prime on Binary Life. If you are new to the channel, Binary Life is a channel that teaches new developers how to code and approach algorithm problems, so that you can have a thinking process and how the solutions come to life. So today we're going to be solving next prime. Now this is a very interesting algorithm, and you are going to see why. Because I did not succeed to completely solve it. Like, my solution is correct, but I don't validate all the code wars. I don't get all the green color validation because of timeout. Timeout is something you get when your solution works, but it takes so much time, and hence it's judged not efficient. But as you can see, many people are feeling like just 30% are succeeding this challenge. So I'm going to share my solution, and I'll be hoping that through the comment section someone can bring ameliorations on how to tweak it to be fast, and so that we can actually validate this scatter. But you can get the thinking process behind the way I approach it, and I think you'll be good to go. Now we have to get the next prime number. That's the exercise. For example, if we're given 5, we need to get the next prime number after 5 is 7. Prime number should be 2, 3, 5, then 7. From here, if we're given 7, the input as 7, we'll probably get like 11, the next prime number. So here we're given 12. The next prime number after 12, after the figure 12, is 13. I think you get the logic. Now this text editor, this is my solution, is actually a small window. I've copied the whole thing into a text file so that we can get a larger screen, and I'm going to do a walkthrough so that you can understand how I approach the problem. Now the first thing you have to understand is from the way I approach my problem is an algorithm called the sieve of Eratosthenes. Now I'll open this. I'm going to link to you this amazing tutorial, prime number sieve of Eratosthenes by Region 10 ESC, which is a channel that describes the algorithm. Basically, it's an algorithm that is used to generate prime numbers. So I use the core of that channel, explains the logic behind it. So from the logic, I got the algorithm that generates prime numbers. Now if we come back to Code Wars, you are going to notice that the name of this kata is next prime, which is the core function of our solution. So this is the core function below. Now everything above are just utility functions that are used to be called inside here, like the sieve of Eratosthenes, which is the very first algorithm. I have a sieve and I have a search. Now sieve generates primary numbers, as you can see, using the concept of sieve of Eratosthenes that you are going to learn about if you watch the video I just showed you on YouTube, which is present on my description below. Now it generates a list of prime numbers and inserts inside these integers. Maybe I would have called it prime integers if you wish. So it generates it and puts inside integers, and we are asked to give the next prime number, which means the number that was given as an input to the main algorithm, I have to pass that number. I have to generate all the primary numbers up to that number, and probably go an extra mile because I need to get the next primary number. That is why I have a constant that I've just pulled out an extra mile number out of the box, 70. I can pull any number. I just picked 70 random. So I'll generate the sieve of Eratosthenes of the n that was given as a parameter plus the extra mile, so that I can pick the next prime number from there. Now, why do I pass this n again as a second parameter to this function? Because I want to use it as a reference point. I want to use it as a reference point when my list of prime numbers are generated, that I can search for in my list, and then I get the next number. That is why I call this second parameter given here. So after generating my my prime numbers inside the integers values, I now call the search function that search inside the integers array. It search for this given number, which is that second parameter we're talking about. We're searching for this number so that we can get the next number after this given number. Now that is where the search algorithms comes in place. Now the search algorithm, I try to get inspiration from the binary search. This is not pure binary search, this is just a basic idea behind it. Now when I get a list of primary numbers, starting from prime numbers from 2 up to n plus 1, when I get a list of the prime numbers, they are already sorted because they go incrementally. So the search algorithm is going to look for, you see, search algorithm takes two numbers, the array and the number we're searching for. So we're going to cut the array into the middle, and then we're going to see if this number is on the lower end or on the upper end. If it's on the lower end, that's if it's smaller than the middle, and then we are going to search from 2 to the middle, because 2 is the first primary number. 2 to the middle, and when we find it, we are going to return. When we find this number to find, we are going to return the very next one we see. Now, like I told you before, I'm just explaining the logic, and I'm not going through the details of the algorithm, but I think you get the logic. Now, if the number we are finding is bigger than the middle, then we start from the middle and end at the end, hence this for loop. And then we are going to find the next algorithm and return. So that's, and normally these binary searches are like a recursive algorithm that keeps breaking down, but I just broke down the initial array just once, and I start looping from the beginning to the middle, or from the middle to the end, and that works for me. And when I copy the solution here, it passes the test, and when I run the final submission, sorry about this, you can see it take quite some time. That's because this algorithm is heavy on very huge numbers. Like you can see, I passed this is crazy. Okay, you can see I passed the whole 112 tests. I failed 0. The exit code comes from execution timeout. That the algorithm took too long to run on very huge numbers. That's 1.2 seconds. And you can see as we keep going ahead, it becomes very complex to do that, because the numbers are getting bigger and bigger. So on the description, I'll put a link to the GitHub code here, and I'll put a description to the description of the sieve of Eratosthenes algorithm, and probably a description of a binary search algorithm. And then maybe you can, through the comment section, give me hints, present your own solution on how you did to finally pass this thing in a very efficient manner without having execution timeout. I'll be pleased. All right, so guys, thanks for watching, and see you in another video for another algorithms. Don't forget to subscribe.